So my goal here today is to share with you a number of lessons that we learned from building these systems and how we solve particular problems. Now, before I go much farther, I should just put out a quick warning. This talk does contain some examples of abusive chat that you might see in a video game. So view at your own risk. So in video games, players occasionally abuse each other during text, in text. And at Blizzard, we thought it was very important that we could detect when this is happening so that we could either prevent it or action it. But there are a number of problems. First, players are speaking in many different languages. They're often not spelling things correctly. And oftentimes, they're quite creative in their insults. So based on these facts, we knew that simple solutions by themselves just wouldn't work. So after careful consideration, we found that there were 5 specific problems that we needed to solve in building an abusive chat detection system. The first was that players speak in non-standard text very frequently. Some examples. And so we found that our solution to this was to choose specific deep learning or deep neural network architectures that could handle this text. The second was that players are speaking in many different languages. They're speaking across different nations. And so meanings change from place to place. So for example, you might have a player speaking in one language, and then when they decide to insult you, they switch to another. And our solution for this was to build end-to-end architectures that could handle both language switching and detection of abusive chat. The third was that gamer speak changes over time. Memes change, lingo changes. If you change your game, what people are saying about it may change. And the solution to this was to have what we call an active learning or human-in-the-loop system that is able to update the model as the conversation changes. The fourth was that some players are going to try to get around your system, whatever you build. And again, having an active learning system in place, so they'll try to do things like say, does this particular weird spelling trigger it, as an example. And having an active learning system in place allows us to continually update the model as people find new ways to try to get around it. And the fifth issue that we had to get around was cultural relativism, meaning that words that people use and how they say them can mean different things in different parts of the world. And the solution to this was to keep our players in the loop. In other words, we would let them help us decide when things were offensive and when they weren't. So for the first part of my talk, I'll be diving deep into our deep learning architecture and our machine learning solutions. So for this particular problem, we used an approach that's known as supervised learning. And it works like this. You collect a large amount of text, which has been labeled, some of which is bad, kill yourself, not so good, or pretty good, like, hey y'all, what's up? It's pretty good. And you can feed it into a machine learning algorithm that learns all the relationships in this text. And then it's able to take new examples that maybe it's never seen before and output a prediction. Go kill yourself, or go hang yourself, probably bad. And more specifically, for this problem, we used to choose deep neural networks, or deep learning. Now, a lot of the details in terms of how you train a deep neural network is beyond the scope of this talk. But I have included slides at the very end for anybody who wants to dive deep. They can see some of the resources there that are available on the internet to start learning. But understanding the basics of deep learning are actually well within the scope of anyone who's finished their second degree in a computer science bachelor's degree. If you know a bit of linear algebra, calculus, a bit of graphs, you already have most of the fundamentals you actually need to start diving into deep learning. So at the simplest level, a deep neural network is a graph. You have data, and you're passing the data along each node. And at each node, you're doing a learned linear transformation with a nonlinear transformation, and then passing that information to the next node until we output a prediction. Now, before we went deep into deep learning, we had to consider a number of other simpler alternatives. Because after all, building a deep neural network can be expensive, you need a lot of data, it can be time-consuming. So one of the first alternatives we considered was, what if we just look for simple keywords? FU versus FYA, as an example. The problem is that just looking for the word like the F-bomb, for example, doesn't capture this context. FYA means something different from FU. You might say, OK, well, what about a bag of n-grams? Combinations of words. We can look for all these different combinations. But the problem is then we have a data sparsity issue, where many different combinations don't occur very frequently, and it's hard to learn from them. And both of these approaches also suffer from other common approaches where you use a dictionary of pre-made words, which is to say that there are going to be many, many different ways that people misspell these words intentionally or otherwise, and you're never going to be able to capture all of those misspellings. Now you might think, OK, well then I can use regular expressions. After all, that's what it's designed for, looking for wildcards and things like this. But there's two problems with that approach. First, you have to know exactly what you're looking for ahead of time. And second, your players are always going to be able to poke holes in your regular expressions faster than you're able to keep up with modifying them. So we knew we needed a system, a deep learning system that could do at least three different things. First, it needed to be able to understand the sequential relationships in text. Because after all, words don't mean as much by themselves as when you put them together. They modify each other. Go kill yourself means something considerably different from go kill that monster. He should probably turn his gun on himself. Nothing in this phrase, no word in this phrase by itself is particularly bad. It's only when you put it all together that it becomes problematic. Second was that we knew we needed a model that could understand relationships at the character or symbol level, like A, C, B. Because people can spell things in different ways, and they can mean the same thing. Third was that we needed to have a system that could understand some of the context in which players were saying things. Because, after all, it may be OK for players to have private banter among their friends, but not abuse in a public space, and certainly not harassment of strangers. So to solve these problems, we devised the following model architecture. And on this slide, I'm going to be going into a little bit of detail in each section, and then I'm going to be expanding out each part of it over the next few slides. So we start with our player text. And then we pass it into our character level embedding layer, which is able to handle similarities in how characters are used. At versus the A, for example. And we pass it through a set of convolutional layers, which is very good at detecting character engrams, words, and short phrases. And then finally into our recurrent layer, which is able to handle long-distance relationships between text. And then a fully connected layer, which allows us to do multitask predictions. All right, let's dive deep into these. Starting with character level embeddings. So if anyone here is already familiar with, say, Word2Vec, they're already somewhat familiar with embeddings. So simply put, an embedding is a way to map a categorical value, such as the occurrence of a single letter, to a real dimensional space. By doing so, we can encode contextual relationships and similarities between the use of, say, characters. So for example, if people are replacing the number 3 with E, or vice versa, and that happens frequently, then the embeddings will encode that. And it also reduces some of the data sparsity issues you would have if you were using categorical values instead. And finally, and perhaps one of my favorite reasons for using embeddings, is because it allows us to stop worrying as much about what the language that someone is saying in up front. So for example, if I was to build a model and parse text for English versus Chinese, and I was building a model that worked on the word level instead of the character level, I would have to do very different pre-processing on that text up front. But instead, by building a model that understands things at the character level, I can treat both of those languages the same numerically. And the math behind embeddings is pretty simple. In your model, you're learning weights for an embedding matrix here on the right, which when multiplied by a one-hot encoding of your text, in this case, for example, a letter, it results in your embedding vector. So a little bit more concrete, for example, we have a weight of embeddings, which are all real values. And our one-hot encoding for, say, the letter C, maybe in this case, would be a vector of zeros with a single 1 at the third index. Multiplied together, now we have a representation of the letter C in a real dimensional space. All right, next up, convolutions. Now, convolutional neural networks are very frequently used in the image processing or computer vision domain. But it turns out they're also very useful in the text domain as well, for a number of different reasons. One of which is that old school machine learning required a lot of upfront pre-processing and what we'd call feature engineering. This is a way to construct your data by hand, usually, in a manner that then the algorithm could learn from. With the advent of advanced techniques, for example, like convolutional neural network, instead, you can have the algorithm learn those features itself. So for a convnet, in our case, basically using what you would call a feature detecting kernel, and it's looking for different character sequences that may be of interest to the model. For example, maybe it's looking for something that's kind of like FUC, but it doesn't necessarily have to be exactly that. And you slide the kernel over our text, and at every time step, we get a representation of those features in the text, down here with Z. And typically, we're not just using one kernel, but we have many different learned feature detection kernels, each looking for different aspects of text. And typically, you're not just using one convolutional layer, but you're often using many convolutional layers, where, for example, the first one may be looking for particular character engrams, and the second one is then looking for combinations of those combinations of characters. Third, we then pass the output of these convolutions into a recurrent neural network, which is very good at handling long-distance relationships in text, how words modify each other across, for example, an entire sentence. And at a high level, a recurrent neural network is learning a set of relationships between these sequence. So for example, here we have our text, hello noobs, and we have a set of recurrent cells, and every cell you can think of as a small neural network itself, where the weights are shared across each cell. And you pass the current input, H in the first case, E in the second, which then combines the learnings from the previous cell, or the output of the previous cell. Here being a more compact representation of that. And there are a number of different recurrent neural networks you can use, such as an LSTM or GRU. But at the end of the day, they all work somewhat similarly. And for the last step, we then feed this into a set of fully connected layers, which looks very similar to the neural network that we saw at the very beginning of the talk, which then allows us to do what we call multitask predictions. And so by having a somewhat complicated architecture like this, we're able to use the same model to predict many different things, such as language detection, what language are they saying, whether or not it has abusive text. We can also look for whether or not there's hate speech in there specifically versus sexism versus threats of real-life violence. And by having a single model do all these things, there are a number of different advantages. The first of which is just that we need less compute because we're running fewer models. The second is that we reduce number of compounding errors that may happen if you start stringing models together. So for example, if you have a language detection model working by itself that says, oh, hey, this is English, when in fact it's another language, and then it passes that text along to an abusive chat detection algorithm that's only for English, now you've made 2 errors instead of 1. And finally, it can handle language switching. So in certain regions of the world, players are often speak multiple languages in their game. And this way, we can have a single model that doesn't actually mind if players are, for example, switching between Spanish and English on the fly. So in summary, from the architecture side, we chose a deep learning approach because it can handle many of the unique challenges for player text. Second, we used embeddings because it handles similarities between character usage. Convolutions, because it lets us learn features of character engrams within the model. And recurrent neural networks, because it allows us to learn long-term relationships in the text. And then having an end-to-end multitask model allows us to avoid multi-language error compounding and allows us to handle switching across multiple languages. So that's the model. But it's not enough to just have a model. You can't just set it and forget it. Because like I said at the beginning of the talk, language changes over time. What people are saying changes over time. So for example, first, text is being drawn from a non-stationary distribution. In other words, what gamers are going to be talking about changes over time. Second, you're going to have what I would call system antagonistic players, players who are trying to get around the system. So once you launch a model, it's important to watch out for things like this. It's important to monitor how well the model is doing. And there are many different metrics you can use, but one of my favorites is this, which is asking the question, for a single model, what is the probability that when a player makes a complaint or a report, the machine learning algorithm says, no, I don't think that's a problem. And what you'll see is that if you keep the same model, those errors will increase over time. And if you dive deep into what players are saying, as we've done, you'll see that there are actually new words being introduced to your corpus, either because you're changing your game, you're adding new maps, new heroes, etc., or just because the landscape is changing. In this case, we saw that on average, after we launched a model, there were about 30 new English words per week. So our solution to this is what we call our active learning system. So we have our chat classifier, and as it reads potentially toxic chat, it puts it into a results table. And then from that results table, we have what we call a text selection engine, which is looking for different pieces of text that we think might be able to improve the model. And the text selection engine specifically is looking for a few things, one of which is text that we believe is very abusive, but players aren't reporting it. Text that the model thinks isn't abusive, but players are reporting it. Text that the model might be confused about, so it's very near its decision threshold. There are some other experimental methods you can use to estimate how much information you think you'll gain from adding particular samples, as well as just a random representative selection of text to make sure the model doesn't drift too far away from the actual population. And from these selections, it puts it into our in-house annotation tool, which we've built, which looks something like this. This is an actual screenshot, in which our customer service representatives then go in, label text, and tell us for sure whether a particular bit of text is abusive or not. And then if we like, we can also draw text from the penalization system as well. So when a player is penalized, sometimes they appeal it. They say, hey, I don't think this was right. I don't think you did me right. And then upon appeal, if they're right, then we can add that text back into the annotation tool as well. And from there, once we have enough samples collected, we can then go and update our model, keeping it fresh. So for the last section, I want to talk a little bit about how we use this system to empower our players. Now, you might think, OK, we've got this model. Now we can just have an autonomous AI that's running all the time, looking for bad chat, and then bring the hammer down when it sees something bad. But that's not what we do. And it's not because I don't have confidence in the model. I actually think it works very well. But like I said before, our player community is truly global. And different things are offensive to different people in different parts of the country, or different parts of the world even, and even on an individual basis. So instead, what we do is we wait for the machine learning algorithm to validate reports. So we wait for a player to say, hey, this guy over here, he's being really offensive. And then the machine learning algorithm kicks in and reads that and says, oh, yeah, that does seem kind of offensive. OK, let's take action now. And this way, we can circumvent many of the issues where, for example, this guy says, oh, these two people are talking, and for whatever reason, it's not offensive to them, but it may be offensive to other people. All right, to wrap up. At the beginning, I stated that we had 5 problems to solve. First was non-standard text. And the solution to this is choosing the right deep neural network architecture. The second was that we have multilingual, cross-national conversations occurring all the time. And having an end-to-end model architecture that's able to understand both differences in language and toxicity allow us to deal with this. The third being that gamer speak changes over time. And the solution is to have an active learning system that is able to keep your model fresh. Fourth is that players will try to get around the system. Some will, not all. And again, having an active learning system that's able to keep up with changes helps us keep our model fresh. And fifth is the cultural relativism. And by using player input combined with the algorithm, we can avoid some of these issues. So to date, this model has been a big success internally in terms of dampening down on abusive chat in our games. We currently support 11 languages and dialects. Since launch, we've seen a 59% reduction in reoffense rates, meaning that when someone offends, they're less likely to do it again now. This is approximately 2,100% more accurate than previous systems that we were using that were not based on machine learning. And overall, we've seen a 43% reduction in the amount of abusive chat in our matches. So, as promised, there are a number of resources online for learning deep learning. And I would encourage people to go to any of these great sites in order to start digging in. Thank you.